require a ton of what we've done already. It's kind of a new concept in a way. So we are going to start Unit 6. It was about solutions and everything like that. I had these on there because last semester we had been working on a performance assessment, so you don't need to worry about this slide. All right, solutions chemistry. A solution is a stable, homogeneous mixture. What is a homogeneous mixture? Anybody have an idea? Correct. Mr. Carter, it is a mixture of the same type. Two words are going to be used over and over and over and over and over and over and over in here. Solute and solvent. You absolutely need to know the difference between those. A solute is the substance dissolved in the solution. A solvent is what is doing the dissolving. Our most common solvent in here would be what? Water. Water is going to be our most common solvent in here. Most commonly, water. So an example would be if you have a soda. For those of you that prefer called soda, I would call it pop, but whatever. Your solvent would be your sugars, your dyes, your CO2, all of your flavorings, whatever. Your solvent, like we just talked about, is going to be water. Water is your most common solvent. And you are going to see tons of graphs in this unit. If you're not comfortable with graphs, I would recommend coming in and speaking with me sometime, because graphs come in handy. So solubility refers to the solute's ability to dissolve in the solvent. So we'll talk about that. If I take, and I have just a tiny little 5 mils of water, do you know if I can take and dump in a pound of salt and have all of it dissolve? Probably not. Because those water molecules are only able to rip apart so much of the salt. They're only able to dissolve so much of the salt. So solubility refers to how much solute is able to be dissolved in a solvent. And everything has a different amount that can be dissolved in water. I can dissolve a lot more sodium nitrate in water than I can, say, potassium chloride. And this is what we'll start working with in this unit. So if something is said to have high solubility, it dissolves easily. We are able to easily dissolve it in water. So if we were to go through and we kind of look at this graph here, something with high solubility would be ones that have a lot dissolved in water. So you'll see here along the left side, along the y-axis, solubility of stuff. It is how many grams of it are dissolved in 100 grams of water. So stuff with high solubility would be like my sodium nitrate, or my calcium chloride. Then it's saying I can dissolve a ton of those in 100 grams of water. Things with low solubility, things that do not dissolve very well, would be like my potassium perchlorate, so KClO3. That is an example of something with low solubility. It is not dissolving very much in our solution. And trends of solubility. To help understand the solubility of a gas, ooh, this is a fun one. This is where it gets kind of weird for students. To help understand the solubility of a gas, most substances are more dense at a colder temperature. I think most of us can agree with that. So at colder temperatures, the gas is more dense and therefore more can fit into a liquid. So when a liquid is colder, it can actually have more oxygen or more gas dissolved in it. What you got there? So, how many of you in here go fishing? Ooh, really? I'm impressed. Last semester I had like 3 students, and then I had one kid who goes fishing literally every day, so he made up for the rest of us. So when you go fishing, fish often like to hide where? Do they like sunny or shady areas? They like shady areas. The reason that they oftentimes are like shady areas is because Is the water going to be hotter or colder in a shady area? Colder. Guess what? In colder water, there is more oxygen gas dissolved. There is able to be more oxygen gas in colder water. That is why the fish will oftentimes hide in those areas. Or when it starts to be summer and the fish slowly keep making their way further and further from shore, is because there's going to be more oxygen at those areas. So in a colder liquid, you can dissolve more gas, which is kind of the opposite of our solids. So you'll notice on our x-axis here in these graphs is temperature. As you increase the temperature of something, as you increase temperature of solids, you'll notice that we are able to dissolve more and more and more and more and more of our solute. However, gases, on the other hand, as your temperature increases, as our temperature goes up, we are actually dissolving less gas in that. So it works a little bit differently. At higher temperatures, it is because the gases boil out, just like when you boil water. So just think of those real-world examples for when you're trying to figure out, do gases or solids dissolve in better or lower temperatures? So solubility of a salt increases as temperature increases. Solubility of a gas decreases as temperature increases. So they are a little backwards of each other. And here is kind of just saying the same thing. As temperature increases, solubility increases for a salt. Remember, salts are going to be ionic solids. Yes, when this says salt now, it is not referencing only NaCl like our normal table salt. Salt is pretty much any ionic compound. And ionic compounds are made up of what two things? A what and a what? Kind of a cation, anion. It is a metal and a non-metal. Metal and non-metal is an ionic compound. Something from the left side of your stair-step line and something from the right side of your stair-step line. Solubility of gas, on the other hand, as temperature increases, solubility now decreases. As pressure increases, solubility increases. And as amount of solvent increases, solubility increases. And we will, again, beginning unit, always throw a ton of stuff at you, and then just kind of change it up. It starts to make more sense as you get more exposure to it. So we'll get you practice with all this, and it'll make more sense. And let's see here. 3 types of solutions. We have unsaturated solutions. Unsaturated means that more solute could be dissolved in a solution. Thank you, sir. Yep. You know what? We'll just stop here. We'll stop here. That's good. We'll cover this later.
Are we doing an activity?
So, if you are ever looking at a chart, please note there's a solubility of salt in 100 grams of water. If you are ever above the line, it is said to be a supersaturated solution. If something is directly on the line, it is saturated. It has to be 100% exactly on that line. It is a saturated solution. If it is below that line, it is said to be unsaturated. And the reason for that is, let's pretend that I had found my salt. That's what I was really looking for. If I had found my regular KCl, well, if I went through and we're sitting at a temperature of probably 25 degrees Celsius, if I added in only 10 grams of my potassium chloride, I would be sitting at this point right here. So I would have had an unsaturated solution. I would have 10 grams of my potassium chloride in my beaker, and I'm at about 25 degrees Celsius, so I would be unsaturated. Saturated is when I took and I just dumped a ton in there. I poured in a ton of that, even if I added in more, even if I added in 80 grams, that doesn't mean that I'm suddenly super saturated. That doesn't mean that I'm suddenly up at this point. Because we're talking about the liquid itself. This water itself has dissolved all that it can at 25 degrees Celsius. So even if I dumped 80 grams of solid in there, I would still only be at this point. I would be at my saturated line. Because the water has a maximum amount of solid density. The way that it would get super saturated is if I start to heat that up. If I took the solution and I put it onto a hot plate, what's going to happen is my solution is going to follow this line. It's going to go up and up and up and up and up because let's say I increase my temperature all the way to 100. So now I'm going to reach this point. And of that 80 grams that I have thrown into that beaker, the water itself can now dissolve more of that. It can dissolve up to almost 60 grams. I'm still not a super saturated solution. Right on the top. To make it super saturated, I need to take that solution out and throw it in ice bath to cool it. But what's going to happen is it don't actually fall out of the solid doesn't fall back out. It just dissolves. So as I bring that temperature back down, as I cool that back down to room temperature, now I can have more of that solute dissolved in there. Linear units seem confusing when you first start. That's why what it is I'm talking about. Keep in mind, the only possible way to ever get a supersaturated solution is at some point in that solution, right? We have to increase the temperature and there's the only possible way to get a supersaturation. So we look at sulfur chloride. Above the CaCO2 line would be a supersaturated solution. On the CaCO2 line would be saturated and dissolved. And you will get plenty of saturation. If you understood what I was just talking about, you're able to follow along. Nice work. If you weren't, I can sleep. Hopefully after today when we get started with the lab, it will make a little bit more sense. You know what? That might actually be all we need to do for today, as far as notes go.
Okay, so we have spent the last, yesterday we talked about solubility graphs, and we learned that if something is above the line, it is supersaturated. Only way a solution can become supersaturated is if it is heated up and then cooled down. It has to be heated and then cooled. Just heating a solution up does not make it supersaturated suddenly. It has to be heated and then cooled in order to be supersaturated. If it is directly on the line, if as much as possible is dissolved in that liquid, it is called saturated. So even if there's a bunch of solid sitting at the bottom of your beaker, if there's all this solid sitting down there, it is still a saturated solution because that means up here in your liquid, there is a bunch of it dissolved, and your liquid is holding as much as it possibly can. So when we look at this, this is talking about the liquid, not necessarily the entire beaker, but your liquid portion is saturated, is holding as much of the solid as it can. And then unsaturated means that the liquid itself would be able to hold more. So unsaturated would mean you have your beaker, and there's just some random crystals dissolved in there. Okay, now we start talking a little bit about math and solving for amount of solute versus solvent. You will notice on the graphs that we have talked about so far, it is always how many grams of a salt can be dissolved in 100 grams of water. Are we always dissolving in 100 grams of water? No, sometimes we dissolve in 50. Yesterday we dissolved in what? 10 milliliters or 5 milliliters, something like that. So would this graph apply exactly to how much could be dissolved? No, because this graph is talking about in 100 grams of water. We don't necessarily always dissolve in 100 grams of water. Sometimes we dissolve in 50. Yesterday we dissolved in 5. So it kind of varies. So how do we solve for how much could actually be dissolved then in, say, 5 grams of water? Well, what you need to do is take your grams of solute on the graph, divided by your grams of solvent on the graph, and this is generally indicated on the y-axis. Usually it is per 100 grams, just like this previous graph was, but it's not always per 100 grams. So you always need to check this value. When they're giving you these numbers of how many grams of a salt could be dissolved in water, you need to check how many grams of water that is dissolved in. For the most part, they're generally 100, but it can vary. So you take your grams of solute on the graph, divided by your grams of solvent on the graph, is equal to grams of solute desired versus grams of solvent desired. Or another way to say this is grams of solvent used. So how much you actually used in your procedure. So if grams of solvent desired is not specified, assume it to be the same as grams of solvent on the graph. And that is when you are solving for problems. And again, this will make more sense when we get to it. And then next, use your above average algebra skills to solve for the missing component. So here's an example. What is the maximum amount of sugar that could be dissolved in 50 grams of water at 80 degrees Celsius? So we look at our graph and we notice that all of these values are per 100 milliliters, or 100 mils of water is also the same as 100 grams of water. So all of these values are per 100 mils of water. So looking at our equation, we have grams of solute on the graph divided by grams of solvent on the graph. Did I just put all this? Oh, I did. I'll put all this down here. Cool. So our grams of solute on the graph, how many grams of sugar could be dissolved in that water? Well, at 80 degrees Celsius, we find out that I can dissolve about 360 grams of sugar in 100 grams of water. And this one's easier for some of you. You're like, oh, well, if I have half of the water, I only have 50 mils of water. Obviously, it's just going to be half of the half your amount that could be dissolved in there. You're like, oh, that's 180. But what if I suddenly gave you 74.2 mils of water? Doesn't become as it's suddenly not as intuitive as 50 is. So I'm starting you off with an easier one. So we take our 360 grams of sugar, because that's how much could be dissolved per 100 grams of water, and now we're solving for, I have 75 here. I must have done this for a different one. Let's just change this. I apologize. We'll make this harder than it was. Now I'll do this for 75 grams of water. So change that to 75 grams. I apologize. And now we're finding out, well, if I only have 75 grams of water, how much sugar could I dissolve? So then we have X grams. So when you go through and solve for this, you have to use your above average algebra skills. And we need to solve for X. What is X going to be? Well, how do I solve for X? How do I get X by itself? We need to multiply each side by 75. So we would multiply this side by 75. Cancels out, cancels out. We take this side times 75, which is what we have done in this step down here. That helps us solve for X, and we find that X is 270 grams of sugar can be dissolved in 75 grams of water at 8 degrees Celsius. And you'll notice how, as always, your units are canceling out. Your grams of water cancel out with grams of water, and you're left with grams of sugar. This is a good reminder that your units will always, always, always get you where you need to go. You want to solve for how many grams of sugar could be dissolved in 75 grams of water. You end up with units of grams of sugar. Did I have this bottom part on your notes?
Yeah.
I did, okay. I just want to make sure, because I remember I had gone through and changed this, so. Is this making sense? Good. Okay. So I know the last time I didn't have this slide and it was more kind of confusing for students, so I was hoping that this would help it make more sense. Big thing is making sure that you are utilizing this equation and following it properly. So take what you need and what you want to have. So let's practice more. What is the maximum amount of grams of potassium chloride that will dissolve in 100 grams at 50 degrees Celsius? I'm gonna let you guys take a minute to do this one. Okay. So when we do this one, this is kind of a trick question in a way. Maybe you're making it more challenging than it needs to be. If we're solving for it per 100 grams of water, what is our chart telling me the solubility per? It's already per 100 grams of water. So all we have to do on this one is go through, find 50 degrees Celsius, that's on our x-axis. We go up to KCl. We draw our line over. And you get an answer of about 42 grams per 100 grams of water. Or for those of you that went through and you did it by solving this, that's awesome. Well, you'll see you're like, all right, there are about 42 grams if you did 41 or 43. I'm not going to be picky. If you had 42 grams of potassium chloride per 100 grams of water, well, again, this is the values coming from our graph. Then we do is equal to and how much we want. Well, I want to know how many grams of KCl per, and the information we wanted to know was per 100 grams of water. So then we can plug that in, per 100 grams of H2O. Well, guess what? If I go through and I do my algebra, and I multiply this by, again, 100 grams H2O, cancels out. Sorry, that all cancels out. And then you multiply this side by 100 grams of H2O. Because remember, whatever you do to one side, you can do to the other. Hey, guess what? Those just cancel out, and you're still left with your 42 grams of potassium chloride. This one is a little bit of a trick question. If it's already per 100 grams of water, if your amount that you need is the same as on the graph, you just have to look at the graph. Is 75 grams of lead nitrate and 100 grams of water at 50 degrees Celsius unsaturated, saturated, or supersaturated? Welcome, Sariana. So I will give you about 20 seconds. Please try this one out. Should not take you much more than 20 seconds to solve. All right. So to solve this one, is 75 grams, and we need to look at what we're talking about. So in this case, we need to label, this is our solute, this is what's being dissolved. 100 grams of water is our solvent. And then we have a temperature of 50 degrees Celsius. So what I would recommend start off doing is just figure out, okay, well, at 50 degrees Celsius, how much lead nitrate can be dissolved? So we come over to 50 degrees Celsius, and then we work our way up and 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 up. And then we hit our potassium nitrate line. This is our potassium nitrate line. So we hit this point right here. And then we go through and figure out, well, 75 grams of lead nitrate. So 75 grams lead nitrate would fall somewhere right around here at 50 degrees Celsius. So is this unsaturated, saturated, or supersaturated? This is how much I would need to be saturated. So that would be my saturated point, and that is at, what, roughly 85 grams at 50 degrees Celsius? 85 grams at... Do we have 85 grams? Nope. So are we unsaturated, saturated, or supersaturated? We're unsaturated. We're below the line. So this is going to be unsaturated. Sorry, my spelling sucks. We're unsaturated. And how many grams of NaCl are required to make a saturated solution containing 200 grams of water now at 90 degrees Celsius? All right, again, I will give you some time to solve this one, and I'll walk around and try to help you. So how many grams of NaCl are required to make a saturated solution? So now you need to think about where would a saturated solution be, containing 200 grams of water at 90 degrees Celsius. And hopefully that kind of makes sense, right? So if I have 100 grams of water and I can dissolve 40 grams of salt. Well, if I have 200 grams of water, does it make sense that I can dissolve twice as much? Yeah, that would make sense. And how many grams of CaCl are needed? Let's change this. Let's do a more challenging one. Let's say I have, how many grams of CaCl2 are needed to make a saturated solution in, let's go 37.6 grams of water at 10 degrees Celsius. We'll make it a little bit more challenging for you. Hopefully it really shouldn't be any more challenging because it's just a matter of plugging in different numbers. Change that to 37.6 grams of water though. All right, so when we solve this one now, again, we have to go through and we have to figure out, well, at 10 degrees Celsius, how much calcium chloride could I actually dissolve? So 10 degrees Celsius is here, we follow that up and up and up and up and up, and we find that we can dissolve somewhere around 63, 64 grams of calcium chloride. And again, that is per every 100 grams of H2O that I have. That was just the worst rectangle I've ever drawn. So we take our 63 grams of calcium chloride per 100 grams of water is equal to X grams of calcium chloride per, and now we did it per 0.6 grams of water. So now I'm saying in about a third of the amount of water, how many grams of calcium chloride can I get? Multiply by 37.6, so we can cancel out what's on top and what's on bottom. Multiply by 37.6. I really need to work on handwriting. That's CH2O. And then you get an answer, what'd you get, 23-ish roughly? Somewhere around 23.1 grams calcium chloride. Okay. When we do the lab today, this is the equation you will be wanting to use. That is why I have so much practice in here. Do I have another problem? No, I don't. So there we go. That is all of our notes for days 1 through 3. That's all we have to do.